All right. The class is on Zoom, so this is also recorded. So you can see the screen also recording on YouTube. Last time I gave the links of the YouTube channel so that you can always see new videos updated there. I'll just post it there. Okay, so we didn't finish the BOD questions last class, so we are going to finish today. And groundwater contaminants or transport will be next class, not this class. Again, homework 3 is extended. Due is tomorrow midnight. Homework 4 will be released. In fact, it's released already. It's due next Thursday. Okay, so that's mostly on BOD and groundwater. So the first 3 questions are BOD. You can solve them after this class, but anything related to groundwater you can't solve until Monday class. Okay, those are 2 questions. So that's on the again, the reason I try to give as much back-to-back homework, because we have 1 week of gap where you don't have any homework, and there we'll practice a lot of these questions for midterms. Okay, so spend a lot of time now, it will help you for your midterms. Again, there are many discussion sessions, TA office hours, so you should have many opportunity to ask questions related to homework. Okay. And this is the homework. As you can, it's very hard to see here on the screen, but this is, I just want to say that this is uploaded. These are all based on BOD. This is groundwater. This is groundwater question. This is also groundwater questions. So those questions, you know how to solve it after Monday class. All right, so the reason we do BOD is for this question, picture that you see over here describe what happens if you have lots of wastewater or waste dumping into a river. So as you can see, fish in the very left corner, fish are very happy because they have enough oxygen. Okay, you see there are different kind of fish, you know, everybody's thriving there. But the moment you discharge some waste, those wastes have so much BOD that microorganisms will eat those BOD. In the process, there is a noise here. It's for me. Yes, because of probably this. See, sometimes it happens, sometimes it doesn't. Try to put it at the bottom. It's a noise from the microphone. All right, so as you can see over here, the moment you add more BOD or the waste that has lots of oxygen demand, the oxygen concentration is going to decrease, and a lot of fish will not survive. As you can see, the only bottom feeder, the fish that strive in eating the mud or things in the mud, they will survive because they don't need that much oxygen. But all the other type of fish will die. And then as it goes beyond 2 ppm, milligram per liter of oxygen, you will not have any fish. You'll see only the stuffs that survive in the mud. And so that's the lowest concentrations. And below, if it goes below even, the life will not survive. Okay. Then, as you can see, the mix, what happens here is that oxygen is being consumed because you have so much BOD. And as the BOD is being also used up because bacteria are using up, there are less and less BOD remaining in the water. That means there are more oxygen. Oxygen is always coming in from atmosphere. So now there is equilibrium where more oxygen coming from atmosphere than the oxygen is being used up. So now it will start rising, and then after a point we'll be back to the previous conditions. So a lot of times, now why it is important? Because imagine you live in this area, or your town is in this area, and there is a wastewater treatment plant that discharges waste here. So a lot of fish will die near your town. So you don't want a wastewater treatment plant far away or certain distance from your home, because that will be very bad for the fish. So that's why this is a problems that being used by many city planner to see exactly where you can discharge the waste, because naturally waste can be the BOD, excess BOD can be consumed, and so you want to put that far away. Okay, so that's why a lot of these questions that you see in the homework is about looking for the distance, a distance at which the concentration is so severe that fish will not die, fish will die. So we are going to solve that question today, but many questions related to BOD. All right, so just to reiterate, BOD is not same as oxygen. Oxygen demand is not same as oxygen concentration in water. Oxygen demand means you have lots of chemicals. Think of chemicals that can consume oxygens. So it's a biochemical oxygen. So as you can see, this is BOD. The waste is BOD. The reason is there are many types of chemicals that can consume oxygen. So you can't really put them into one group. What's the chemical formula? So you can't really have a redox reaction here, because every molecules will have different structure. So that's why we call BODs. That way we can solve these complex different types of pollutant into one group. Okay, and we don't really care about what's their compositions or structures, all that. All we care is how much oxygen is being used up. So you measure the amount of waste based on how much oxygen they can use up. Okay, so that's the reason you see this BOD test is conducted. BOD test is basically you take the waste, you don't know how much BOD is there. You just put them, start with the test, and you measure how much dissolved oxygen being used up in 5 days. So those extra, the dissolved oxygen used up is proportional to the BOD that being used up during that time. So the amount of BOD you can calculate based on the amount of dissolved oxygen is used up. And so those are the amount of BOD used up during that time. But how do you know what is the exactly BOD that was before that? So that's the first challenge. Only things you can measure is how much BOD changed, not what was initially there. So you need some kind of equations to predict what was initially there. It turns out it's a first order differential equations. It's a first order rate, something you already solved. So I'm going to show that how it is done. So that way you can use it a lot of times. So BOD 5, every time you see BOD 5, that means BOD used up in 5 days. It's not the BOD concentration in water. That's the biggest mistake most students do in exam. I give BOD 5, they assume this is the BOD in water. This is not the same thing. Okay. BOD 5 means they take that water, do the testing, and see how much BOD is used up in 5 days. So you can use that to predict what's the initial BOD. So that's the first thing you have to change in your problem. So again, absolute BOD cannot be measured. You can only estimate that based on the how much BOD consumed in 5 days. So BOD 5 test is the only test you can use to predict that BOD. So let's see how to do it. So modeling BOD reactions. The assumption is this is first order. Amount of dissolved oxygen used up is same as amount of BOD consumed. Okay. So whatever amount of oxygen being used up is the same thing must be because of the BOD that depleted during that time, or BOD oxidized. So how much amount of BOD oxidized is basically is saying that change in BOD concentration with time. So that's basically you can write that BOD, let's say at time equal to 0 minus BOD time at t minus t minus 0, or time t, the difference in time. Or I can write that. Sorry, I'm writing it. So it can be any time, and most of the BOD test is it's only 5 days. Okay, so all we are measuring is that how much difference in BOD change in 5 days based on the oxygen. So what you are measuring here is oxygen. You can measure oxygen, right? So that DO2 you measured, and that's the same thing as BOD initial minus BOD final. And then you can predict what's the BOD initial from these equations. A lot of times the notation in the book or everywhere is written as BOD. If you see, right, 3 words. So people write that as L. So anytime you see L, that's BOD. BOD ultimate. The another way to say is BOD ultimate is basically amount of maximum BOD present that can be used up by bacteria, or same thing as BOD. But the moment you see BOD, so the moment you see this is a LT, that means BOD remaining after time T. So that's the BOD in water. Okay. But the only notation that we write BOD is when we talk about BOD 5. So BOD 5 is not the concentration of BOD in water. Okay, so BOD 5 is the concentration change in concentration in 5 days. Okay, so that's basically you are saying delta L in 5 days. That means this is L0 means time equal to 0 minus LT. And here T equal to 5 days. What is initial BOD? That you don't know, but you are going to estimate based on this, because you can measure this one. BOD 5 is the change in oxygen concentrations. Okay. Same thing as DO2. Oxygen demand is basically how much oxygen being used up. So this is what you measure, and this is what you can calculate or estimate. You can estimate that if you know what is this number, right? So that number you can predict based on these first order reactions. So that reaction, if you derive it, basically we did that before. Any first order reaction like that, we did it before. dLT by LT is K dt. And the BOD concentration decrease with time. So that means there has to be a negative sign here. The reason is the concentration of BOD decrease with time. As the time increases, the DLT decreases. They're opposite sign, right? So that's the negative sign there. So if you solve this one, the equation is the same thing as batch reactor. So you can write this one, LT is L0 e to the power minus KT. And L0 is when BOD ultimate at T equal to 0. BOD ultimate at T equal to T. So this is the first order reaction that we keep coming back. So you just don't have to derive again. You just know this is the same equations. So if you put it here, L be L0 minus L0. So if you take that common, so it's get L0 1 minus e to the minus KT. So why it is important? Now this entire expressions can relate BOD 5 with your initial BOD L0. Okay, so that means if the BOD 5 is given, I asked the question, what's the amount of BOD initially present in the water? You can calculate L0. Okay, so the equations that you always use if the BOD is given, L0 is BOD 5 and T equal to 5 days here. Okay. So many quiz questions or not quiz questions, short question will be given BOD 5. You are asked to calculate this, or you will be given this one and you are asked to calculate BOD 5. Everything else will be given, right? K is always given. And the important thing is the K, the unit of K should be 1/day. Okay, that's the unit of K, because here the time is in days. So if the unit is given in a different time, let's say hour, you have to change to day, okay, to use that equations. So this is already derived. So BOD utilized in time T is same as BOD 5. So this is BOD. So if you use this equation, BOD 5 is and if you see this equation, if you plot this equation, this is the amount of BOD in water at different time. It's decreasing with time exponentially because of these equations. And this is the BOD utilized, or amount of BOD used up. Initially 0, then it's increasing with time. This is this. Okay. If T equal to 5, that's a special case. What is the amount of BOD used up in 5 days? All right, so that's the only equation you have to remember is this. Okay. Everything else you already know. So let's solve some example questions. The dilution factor P for an unseen mixture is 0.3. All right, so this is a relative dilution factor. That's from the last class. So if I go back to the last class, we don't need to solve that one because that's a different equations, and let's solve something that's most likely you need for homework. Okay. This is dilution factor. BOD 5 is related to dilution factors and DO initial minus DO final. So this is the equation you use for a laboratory calculation. So this is all about if you test how much BOD. So I'm not going to, let's see. I'm just going to write that equation there so that you know what equation to use. So BOD 5 is DO initial minus dissolved oxygen final divided by dilution factor. So this is P. So that's A. Okay. Everything else is given. DO initial is 9 milligram per liter. DO after 5 days, it has dropped to 0.3. So this is 0.3 milligram, 3.0 milligram per liter. That's DO final. Divided by P is 0.03. So that would be 6 divided by 0.03 milligram per liter. So that's 20, 600, 200. So that means all it means that in 5 days in that test, there are 200 milligram per liter of BOD is consumed, which is basically equivalent as a DO. 200 milligram per liter DO is consumed. Okay. So we express BOD as a dissolved oxygen because you can't really have molecular structures or specific formula. Let's solve the question B. What would be the ultimate BOD? So that means anytime you see what is ultimate, that basically saying what is the initial BOD. So I'm asking you what is L0 is. You know L0 is BOD 5 1 minus e to the power minus k 5 days. So that will be 200 milligram per liter. K is given 0.22 over day, and this is 5 days. So I'll get the answers in milligram per liter. So again, the question here is anytime you see ultimate BOD, that's basically asking what is the concentrations of BOD in water, not what is consumed in 5 days. So this is basically before the test started, what was the initial BOD. Number C, what would be the remaining oxygen demand after 5 days? So it's saying how much BOD remain in water after 5 days. So that means I'm asking what is amount of BOD. L0 is the starting point, initial. What is LT equal to 5 days? Well, that's easy. So you know what is initial and then how much you consumed. So if you subtract BOD 5 in 5 days, whatever consumed, if you subtract that from what is initial, then you get what was remaining. But another way you can write, if this equation is same as because you know that any times the BOD decrease with the exponential function from initial number, and you can get that if you put this value, you can see that it's coming same way. So BOD 5 is, you know, that is L0 1 minus, that's the BOD 5 expressions. If you put that value, L0 cancels, so the only thing you got is this value, which you already knew before. If you see the previous equations, we knew this one. This one, we already knew how to predict BOD at different times if you know what is the initial amount. So in this case, it happens to be 5 days. Okay, so that's, you know, the L0 value. You calculate that, whatever the number, so everything else is given, estimated. So this example is a very good example, calculating based on what you know or what is given. Usually K is always given, okay? And in the short question, mostly in this equation, one term will be missing. So you'll have to estimate the missing term by just plugging the value. So from now on, as you see, will not be asked to derive any equations. You just have to know which equation to use, okay? And as far as derivation, you already know how it is coming from. So one other thing is that BOD, the rate is basically how quickly the bacteria is using oxygen. It depends on the temperatures. It depends on many factors actually. One of the factor is temperature, because in winter time, the temperature is low. Bacteria are not so energetic. So they don't use oxygen as fast as they can use in warm water. So that's why if you have warm water, it stinks a lot faster than cold water. That's the reason you refrigerate everything, because it slows down the rate. So a lot of times the rate constant will be given in a different temperatures, and you have to estimate at different temperatures. So then you can use these equations. KT, it's hard to see, so I'm going to write it here. At any temperature you can predict if you know what is the K at 20 degrees Celsius, because most of the laboratory is in 20 degrees Celsius. The air conditioning in the room roughly is 20 degrees. So that's estimated at 20 degrees Celsius. You just have to extrapolate what that rate would be at different time, at different temperature. So that's this theta. Theta is a constant, T20. So this is at different temperatures. The theta value is given. You can check the book, what's the number, you can always assume that's the same theta. It's usually estimated using a laboratory experiment. Okay. That you don't have to, theta is a constant. Check book, what is that number is. Another thing, this is a kind of quiz questions where how the degradation rate or oxygen consumption rate or BOD utilization rate will change. One is temperature, you know why it is. Then there are a few other things. It depends also on microorganism. Some bacteria are more efficient than other. It's like we are all different. Same thing, bacteria are also different. So it depends on what kind of organism in the water, the BOD consumption will be very different. That's why in the BOD test, they use the same type of bacteria. The inoculant will be same. Okay, that way they can compare across different wastewater. And then also depends on types of organic carbon, because organic carbon is BOD, right? So if you dump a lot of plastic, your BOD is 0, because plastic will not be eaten by bacteria, even though it has lots of carbon. Okay. So the type of organic carbon or biodegradable carbon is also a factor. So another example how you can use what we just learned is basically, it says waste had ultimate BOD. So that means it says L0 is 300 milligram per liter. At 20 degrees Celsius, the 5-day BOD was 200 milligram per liter. So say BOD 5 is at 200 milligram per liter and temperature is 20 degrees Celsius. The reaction rate constant was 0.2. So the K R at 20 degrees Celsius is 0.22 over day. What would be the 5-day BOD of this waste if it is the temperature is 25 degrees Celsius? So what is the BOD 5 at temperature T equal to 25 degrees Celsius? So BOD 5, any BOD 5 equations is basically L0 this is the BOD 5 equations. Okay, BOD 5 equal to what the initial concentration 1 minus e to the power this, right? But this K is at 25 degrees Celsius. In this case, you are not given that K. You are asked to calculate the K. So all you have to do is calculate. That means all I'm asking is what is K 25 degrees Celsius. So that one based on this formula, you know, it's basically K20 theta 25 degrees Celsius minus 20. Theta is basically check the book, what's the number is. Then you get that K and put the value here, you get the answers. Okay, so the only thing that missing was the K value. So that one. (25 degrees Celsius). Yes. One constant. So that empirical constant that determined by laboratory based on what microorganism, what BOD types, all that. But for this class, whatever the number is you see in the book, always use that if it is asked. So this one. Again, these are examples from the book. So the solution is given in the book itself. So I'm just doing in the class. All right, so this is the main thing that we are here for. The why, how do you predict the BOD concentrations once you discharge into waste? Okay, this is the river problem that we are looking for. So this is it's called oxygen deficit model. Means how much oxygen is being used up if waste is discharged into a river, and how far after the waste is discharged, how far from that waste discharge point the oxygen concentration will be the least amount. So that's the That's the danger, right? You don't want that to happen. It's very close to your home. So that's what we are going to predict. So this is just a picture that shows that wastewater is dumped into a river and then it moves as a PFR. So the whole waste is moving as a PFR. So this problem is a PFR problem. Okay. The only difference here, the pollutants is now BOD. As opposed to anything else, you are just using BOD as a pollutant. So you solve this kind of question before, so you can solve many questions like that again. The only difference is BOD concept. So again, it's the same assumption. It's a continuous discharge. So the volume of discharge points or the flow rate is constant. It's a completely mixed system. The moment it mixed together with the river, the concentrations are quickly mixed. So that means you can estimate what concentration of the waste would be after that mixing. Okay. And this is a PFR reactors. Okay, so now, as I said, we are interested in BOD, but mostly because we wanted to know how much oxygen concentration is at different points. Okay, so there what determine the oxygen concentrations? There are two things that matters here, two reactions that determine how much oxygen in water at different locations. Number one, dissolved oxygen will be utilized by bacteria by consuming that BOD. So you have chemicals and that chemical is being utilized or destroyed or oxidized, and as it goes further and further, the bacteria is using up oxygen. So this is what we just learned. Okay, so this because of chemical, the oxygen concentration is going to decrease, but that's true for a closed system. If you see that BOD test that happens in lab, they close it completely, so there is no oxygen coming from atmosphere. So the BOD concentration decreases exponentially. But that will not happen in nature because that exposed to atmospheric oxygen, and atmosphere has 20% oxygen. So the moment it sees that there is a gradient or difference in concentrations, it will start coming in. And how much oxygen coming in is based on Henry law. We learned that last class. You know that from the Henry law constant of oxygen, based on what is the ratio, you can predict oxygen concentration in it could be air to water or water to air. Doesn't matter, the unit will change. The point is this is a constant at a temperature. So that means this is atmosphere, 1 atmospheric pressure. So this is 0.21 atm. So in last class, we remember oxygen concentration in water 0.21. So that means if the maximum amount of DO that can be in water is constant at a constant temperature and pressure. So that we calculated last time at 0 degree, it was around 15 milligram per liter. So this is, if there is no BOD, that's what we expect. You can't go beyond it. But because of BOD, the concentration decreased. That means there is a now positive pressure from atmospheric oxygen to get into water, because you always want it to be in equilibrium to get to this point. So the moment there is a deficit, the amount of oxygen will come from the atmosphere, start dissolving. So now you have to solve two things. One is oxygen is being used up by bacteria, and then oxygen is being supplied by atmosphere. And after a point, the supply is not as much as how much is used up, so that's why it's decreasing with time. And the moment when the BOD concentration decreased to a point where it's not consuming as much oxygen as much as the supply is being taken there, or oxygen is supplied, then the concentration of oxygen will increase. That's what we see. The oxygen sac curve is like this. what it means that the oxygen concentration will decrease initially because the supply is not as much as what is the demand is. And as you go to this point where the supply is always constant, right? So all the time you have the supply chain is, and that depends on the deficit, how much difference in oxygen is there, that will drive that reactions. So that's the only thing is concept. Everything else is you know how to solve it. So I'll just show you how to do it. Okay, so how much oxygen is being used up is same thing as how much BOD is being consumed. So we just solve it. Okay, so rate of oxygenations is same as rate of deoxygenations, means removing oxygen by BOD is same as D. So as you see, the oxygen concentration decreases, the LT concentration, they're opposite, right? So if you have more chemicals, there are less oxygen. So that's why there is a negative sign there. If you try to correlate together, and you know that this value is this, so that's why it becomes positive. So this is already you solve it. So that means you can say rate of deoxygenations and LT you already solved it before. L0 e to the power minus K. So this is the rate at which oxygen is being used up. Okay, that's basically same reaction as BOD reaction, and you did it before. But now the second question is how much oxygen being now is coming from atmosphere. That's the second equation. Then we just combine together, solve it, you get the answers. But before you do that, first you have to, as I said, the waste is being used, waste is dumped here. This is not the waste that moving. That waste is diluted by river. So first you have to estimate what's the actual waste in the river after they are mixed up, right? Because this reaction takes place after they are mixed in the river water. So you know this is LT, this is L0. But what you are asked to calculate is how much L0 in the wastewater. This is L0 in wastewater. What you have to calculate is what's the BOD in the river after mixing, because that's what is going to react with the river bacteria. Okay. So what is the L0 after mixing? L0 is BOD ultimate after waste mixed with river water. Okay. So if you write that equation, basically this is river flow and this is waste is discharged. Okay, so let's say this is QW as waste. That's the wastewater treatment plants. And the concentration BOD in that waste is LW. And then this is river coming, this is river flow. Upstream, you know that this is QR. And the concentration of BOD in the river is, because there will be always some BOD in river water. It's not completely clean. There will be always some organic. And I ask what is the concentration of L0 here after mixing. And you know this one based on mass balance equation. This is a steady, first of all, this is a steady state. steady state for flow and everything else. That's the assumption. And then just mixing is not a reaction, it's just the dilutions. Okay, so when it's just mixed there is no reaction is happening because it only react after it is mixed with river water. So no reactions. So if you do this as make this assumption, that right that point, the mass balance equation is basically Q in, C in is same as Q out, C out. Whatever coming in should be mixed together to become whatever leaving the system. So if you write these equations here, what's coming in is QW, LW, that's the waste coming in, plus mass of waste, mass of the BOD coming through river directly before even the waste is there. So that's QR, LR. Here LR is the concentrations, okay? Concentration term. And then Q out. Q out is basically this two flow mixed together. So the flow rate is going to increase a little bit. So that's going to be QW plus QR. That's the mass balance for just water. And then C out, what is coming out is what you are predicting. So if you solve for L0, just rearrange the equations, you get these answers. So if the question is given, you don't have to solve any of this. You just have to directly write that. Okay, because nowadays becoming more repetitive. You just know how it's coming there. So when there is a wastewater and it says that it's being mixed up, just write the final equations there. You don't have to show how it is gone there. If I ask what is the concentration of BOD after mixing, just start with this. Okay. From now on, every question you don't have to derive everything because you already know the same thing over and over. I'm just showing here so that you know how I get there. In actual question, you can just write this value and plug all the things given to you. Unless I ask to derive in midterm, which I never ask, you just have to identify what's the right equations and put it there and solve for it. Solve for the unknown. Okay. At least this kind of questions. The BOD. From now on, every chapter you don't derive anything. You learn how to derive it in the class, but you don't need to derive that in your homework. All right, let's solve one question before we take a break. A wastewater treatment plant serving a city of 200,000 discharge 1.1 cubic meter per second of treated effluents having an ultimate BOD 50 milligram per liter into a stream that has a flow rate of 8.7 cubic meter per second and a BOD of its own equal to 6 milligram per liter. Deoxygenation rate constant is 0.2 per day. Again, let's see what's given here. Again, always draw the figures. Okay, there is a stream moving. That's the stream. The flow rate of the stream is so Q stream is 8.7 meter cube per second. The concentration of BOD in the stream, so that's, let's write LS, is 6 milligram per liter. And then there is a city, so this is a city that discharges wastewater into that stream at certain flow rate. So the Q waste is 1.1 meter cube per second. And it says its BOD is 50 milligram per liter. So that's L waste is 50 milligram per liter. anytime you read these questions, always see whether it's an ultimate BOD or BOD 5. If it says BOD 5, you have to first calculate ultimate BOD. And that's the one mistake every student, almost everybody does if they don't really pay attention. So BOD, ultimate BOD is actual BOD concentrations. BOD 5 is not BOD concentrations. You are solving for BOD concentration, not BOD 5. Okay. So here you don't have to worry about, because it doesn't say the BOD 5 anywhere. It says ultimate BOD. So then once they are mixed up, the deoxygenation rate in the river is, or which basically BOD used up, KD is 0.2 per day. Assume complete and instantaneous mixing. Estimate the ultimate BOD of the river just downstream from the outfall. Means basically I'm saying once they mix up, what is the BOD? Because they are just being diluted. So you know that one. I'm asking after mixing. You already know from the previous equation, this is the formula, right? So you just write that QW, LW. Here I change the notation for stream. I say QS, LS. Okay, QW is 1.1 meter cube per second times 50 milligram per liter plus QS is 8.7 cubic meter per second times 6 milligram per liter. Then you just add up the flow rate. So it's 1.1 plus 8.7. The unit cancel out, so the only answer we'll get is milligram per liter. And one way to check whether your answer is correct or not, as you can see here, they are being mixed up. So that's going to be diluted. So the concentration must going to increase more than 6. It's going to be less than the waste. Okay, so what are the waste number? 50 milligram per liter and 6. So it's being diluted by a factor of the how much is being mixed. All right, so let's look at the whatever that number is. I don't know the answers. Then it says if the stream has a constant cross section so that it flows at a fixed speed of 0.3 meter per second, estimate the BOD remaining in the stream at a distance of 30 kilometers or 30,000 meters. So let's simplify what is being asked. All mixed up here. Okay, the waste is mixed up, and then it's moving here for another 30 kilometers or 30,000. So you know what is the L0 or the contaminant concentrations at the start. Then that contaminant will move 30 kilometers, and I'm asking what is the concentration after that move there. In the time when it's moving, it's being diluted or not diluted, reacted. So this is a PFR. Basically, I'm asking a PFR question. L is given the length, so I'm going to write it as a distance because this now L is used as a BOD, so the notation might be so different. So I'm just going to write as a D, capital D for distance. So I'm asking what is the L value at 30 kilometers. And the rate is given. Rate is the same thing because you can assume the KD. Okay. So this is the PFR equation. All I'm asking is how much remaining after that whole waste is moving the same speed. So the velocity of water here is given 0.3 meter per second, and the cross-sectional area is not given. All right, so it's a PFR question. So you know what is the concentration of any pollutants when it move in a pipe or a river after a certain distance. So just let's write the equation directly. So concentration at 30 kilometers will be whatever the concentration at 0 . If you look at the PFI equation, is distance times area of the cross sections over Q. Is this correct? There is something somewhere missing. There is a K somewhere, right? It's a K here. Is this the correct answers or the formula? Yeah, basically KT, T is flow rate divided by volume. Okay, so that volume is length times the area, cross-sectional area. So this is Q downstream, okay. This equation, if you divide flow rate divided by area, is same as velocity. If you divide flow rate by cross-sectional area, that's the flux or the velocity. So that means you can write L0 everything else is given. So L0 minus 0.2 per day. Distance is 0.3 meter per second. Oh, sorry, distance is not that. Distance is 30,000 meter. Velocity is 0.3 meter per second. This is in day, this is in second. So you got to change that unit. One day. Oh no. Oh. 1 day is same as how many seconds? That is a big number. Forgot. 24 hours times 60 minutes times 60 seconds. L0 is calculated from A. Then you get the number. So as you can see over here, we are using constantly PFR equation. So there is no new thing here. You already solved this question in homework 3. We are doing the same thing in homework 4. Okay. So it's not any different. The only difference is the concept of BOD. BOD versus BOD5. As long as you understand BOD concept, you should be able to solve exactly same thing without any extra knowledge. So when we come back after the break, we are going to derive the equations for this. We are going to solve these equations and distance. What's the distance here? Then all right. So it's 12:57. Let's take a 10-minute break. We'll see at 1:07. All right, so this is example questions. This was on midterms in 2018. It's a lot of text, right? But what we just solved is exactly same questions. What it says that there is a wastewater treatment plant, discharge certain amount of waste into a river, and you asked to calculate the same thing we just solved. Okay, so it just looked like it's a lot of text because it's just given different things. So a lot of times in midterms, your challenge is not actually solving the problem, it's trying to understand the problem. Okay, trying to understand what terms are what. Okay, and one thing I want to say, this is the problems where 50% students made a mistake by assuming BOD 5 is same as BOD ultimate. As you can see over here, if you see this line, you measure the BOD 5 of the stream water 50 kilometers from the discharge point. So you measure BOD 5. So every time when you try to solve everything, you got to convert that to BOD 5 to BOD ultimate before you do anything. Okay, because BOD is what is conserved, BOD ultimate, not BOD 5. BOD 5 is just a test. How much BOD is removed from the system in 5 days if you were to measure it. So everything else, if you see, sometimes it says BOD, sometimes it says BOD 5, you got to pay attention to that. What I'm asking BOD, it's the BOD, that's the BOD ultimate. If I'm asking BOD 5, you know what that means. You just have to plug that equations and get the BOD 5 from BOD ultimate. So as you see, the questions in midterms are exactly like the example question we solved. It's just a little bit here and difference. So I just want to put it there so that you know this is a question there on the slide. So you should try to solve it after this class because we already solved similar examples. And that way you are prepared to solve at least one question. If it is on BOD, this should be like that. Okay. So in my experience, students who solve all the homework questions and solve it many times, they never receive less than 90% in the midterms. At least in the long question, they all get full credits. The question where they lose point is the concept questions. Concept question is, I'll give you right away here. This is a concept questions because it says how much oxygen can get into water based on certain variables. So this is basically re-aeration rate. This is the amount of oxygen that comes from atmosphere to river at any time. As I said, that what drive it is the deficit, because BOD is consuming that oxygen, so that means the atmosphere, that there is a positive pressure. There are more oxygen in atmosphere than less oxygen in water than what atmosphere wants based on Henry constant. So that deficit, as long as that deficit is there, which is basically deficit is amount of maximum oxygen that can be present in water if there is no waste minus the actual concentration in water. And this actual concentration of oxygen is because of the BOD or chemical in water. So this deficit is what drives the amount of oxygen can dissolve in water. So that's the deficit. If you have more deficit, more oxygen will diffuse into water from atmosphere because it's an open system. But it also depends on, first it depends on deficit, and second it depends on what's the rate at which oxygen can diffuse into water. That depends on how much oxygen, how much water is exposed to oxygen. Because if you see a river water, the atmosphere is just on the surface. So the water on the surface is touching atmosphere, not what is inside. So they are not really touching the atmospheric oxygen. They do not have access to. So the oxygen has to diffuse from water to inside for oxygen to be completely saturated. And diffusion is very slow process. So what you need is actually mixing the water, create a turbulence so that the bottom water will go up. And how that happens in the stream depends on these two factors. If you have higher velocity, there will be turbulence. When there is more turbulence, there is more water coming from bottom to top, so you get the mixing. So that's why if you increase the velocity of water, there are more oxygenations. On the other hand, if you see over here, the amount of reoxygenation rate depends inversely proportional to the height of or the depth of water. The reason is if the river is not shallow, very depth, it takes long time for the mixing to occur. So if you have a shallow river, there will be more mixing because there will be more likely the bottom will come from the top. So these are concept questions. So the type of question I'll ask is, if the river becomes shallow, is this the oxygen concentration going to decrease or increase? Like which questions? So it's coming from this equation. But you don't even need to know the equation. If you understand the concept, you can answer the question and quiz. And same question in midterm question will be just a quantitative. I'll give everything, you just have to calculate KR because you'll be given all those two numbers. Okay. And then also how KR is related to deficit. If there is more rate of oxygen coming into water, the deficit will decrease very fast because you are supplying much faster rate. So you have to think of conceptually all that to answer those quiz questions or concept questions. Nothing in the questions will be out of the slides. Everything on the slide will be everything on the questions in midterms. So if you understand the slides, you should be able to answer every question. All right, so KR is the reoxygenation rate. Again, that change based on the different type of surface water. If you see, if it is a small pond, the rate of oxygenation is very small because you don't have the velocity to mix up. But as you go to a stream which is very turbulent, you can see the oxygenation rate is much higher. Okay, the rate is much increasing. That's because of the depth as well as the velocity of the mixing. Rapid waterfall. That's why anytime you see waterfall, usually that water is very clean because atmosphere, all water is mixed with atmosphere. It's falling in the sky, right? So that's why you can see the rate of oxygenation in waterfall is much higher. In fact, this is the reason. If you see how the wastewater treatment plants are designed, is they are trickling the water on it's called trickling filter. Basically, they put a lot of rocks, let the wastewater slowly percolate on the rock. And that's how it basically helps the oxygenations. A lot of times when you don't have this big rock or the space to make those trickling filter, they just pump oxygen air into it. So they just have a big blower just pumping air into it. And those are very expensive. In fact, 90% of the energy requirement is because of this oxygen supply, the pumping rates. Okay. All right. So now what you know is if I give a question, you know how to get the KR. Usually KRs are given. Okay. All right. Now we have to solve these questions about deficit. Okay. Rate at which oxygen is transferred from air into stream. This oxygen is what driving that oxygen concentrations is the deficit. And deficit is basically oxygen saturation, which is based on Henry law constant. And this is the oxygen remain in water because of BOD. Okay. So now that you know this one, let's solve these questions. Initial oxygen deficit. A wastewater in example 6. Oh, where is example 6? Did I solve it? Yes, we solved these questions. Has a dissolved oxygen concentration of 2 milligram per liter. So DO concentrations. This is DO. The discharge rate. This is the velocity. The river that is receiving this waste, not velocity, this is the flow rate, Q waste. A river that receiving the waste has a DO equal to 8.3. So this is a river. You have wastewater is being discharged, QW is 1.1 meter cube per second. And the concentration of DO, so DO waste is 2 milligram per liter. Then in the river, the flow rate of river is 8.7 meter cube per second. And DO concentration in the river is 8.3 milligram per liter. The temperature is 20 degrees Celsius. That we know what's the term to use. Assume complete mix. In standard mixing, estimate the initial dissolved concentration or initial dissolved oxygen deficit of the mixture of wastewater and river water, just the downstream. So basically I'm asking here, what is the deficit is. Here I'm not asking dissolved oxygen, I'm asking what is the deficit. Deficit means maximum amount of DO that can present minus the actual present. That's the deficit. DO sat you can predict based on Henry law. You already know how to solve it. Okay. If you know Henry law constant at 20 degrees Celsius, you can solve it. Okay. Thus we just did it a few minutes ago. What you don't know is what is the dissolved oxygen concentration just after it being mixed. But that you know already. If you know what the solution is, basically 2 DO is mixed together and becomes something, right? So that's what the DO is here. Since this DO is basically after this DO mixed with this DO. Okay, so there is a stream with very low DO mixed with a stream or river water with a little bit higher DO. When you mix them together, it will be somewhere in between. So that's basically also a mass balance equation. So DO downstream, you can write the same mass balance equations. It's the same way. QW DOW plus Q river DO river this is the same mass balance equation for, if you see the previous times we did this is same equations. The concentration after mixing is basically you whatever input here the contaminant or the substituent you are looking for is DO as opposed to BOD. So again we keep coming back to the same point. So QW is what? QW is 1.1. Dissolved oxygen concentration is 2 milligram. QR is 8.7 meter cube per second times 8.3. So deficit is okay. So now the questions are becoming more repetitive. You already solved the same question before. You are just doing a little bit extra here. The only difference here, this question was the contaminant or the concentration of the constituent is not BOD, just DO. The concept is same. And again, DO sat is concentration oxygen in air (0.21). Then check the Henry constant at 20 degrees Celsius. Okay. And make sure the unit of Henry constant is atmosphere divided by, so whatever that things at 20 degrees Celsius. And the unit has to be ATM. ATM liter divided by moles. Okay. So the answer what you get is moles per liter of oxygen, but you know how to change moles per liter to milligram per liter, because 1 mole of oxygen is 32 gram of oxygen, which is 33,000. So we solved the same question before last class, so we know how to do it. If I show you the last class how we did it, somewhere we did it. Here. We already solved the same questions at different temperatures, plug the value, and they get the answers in milligram per liter. Okay, so the last questions, which is basically the calculating the distance by which it will be very small. And luckily, we don't have to solve these questions. You just have to write the answer. So deficit at any time, deficit over time is a function of two things. How much, what driving the deficit, which is BOD, amount of BOD in the water, okay, the rate at which the BOD is being consumed. So that's here, that's creating deficit, minus the amount of oxygen is coming from atmosphere, which is decreasing the deficit. So these are the two terms we know. So this is basically deficit is the oxygenation rate minus so deficit increase if you have more deoxygenation rate, means BOD is using up the oxygen. Deficit decreases if your atmosphere is providing more and more oxygen. Okay. So you know this value KD LT is L0 So if you see this equation, the variable is D, everything else are constant. KD is constant, L0 is constant, KR is a constant. So there are two variables. So variables D and T. So this is a linear equations, d by dt. So think of dy by dx times some constant time x or y plus some function of x. So this is basically, I can write this one is, or these equations plus some function of t. Okay, this entire thing is a function of time, temperature, time. Okay, because everything else is constant. L0 is a constant, these are constants. So this is just a function of time. Where ft, so ft is basically ft I'm just defining that ft is equal to this. So if you put this equation in the websites where you can derive the solution for this, you'll get answers. Luckily, I don't have to derive because I don't expect that one to do. So this is the derivations. The answer is this. Okay. So anytime you want to calculate what's the deficit, just start with these equations. Okay. Deficit is a function of deoxygenation rate. This is reoxygenation rate, Kr, and then your time, and also the initial deficit. The initial deficit is how much when they are mixed together, which you just calculated in the last example. So if you put this initial deficit there, everything else is given to you. You can calculate how the deficit is changing with time. Okay. And time is basically here, time is, how do you know time? Time is basically how that water is moving. Okay. So that time is a function of distance, how far it is moved in the river. Okay. So if you put this time is basically velocity of distance, or another way to write is where x is distance from mixing point water in river. So that means you can just plot, if you don't know the time, you can just put this value x over time, then you can get the same equation as a function of distance. Okay, so that means you can predict distance if you know that, if you predict deficit, if you know the distance from the discharge point. So if you plug these equations and solve in, not just solve in Excel, if you put this value at different x, you can get different DO or different deficit. So that's exactly that answer is. So as you see over here, this is the same equation. Instead of time, it is expressed as distance over velocity, because usually velocity is given and you know what's the distance from your locations. So this is the mixing point. As you move further and further in distance in the river, the concentration will decrease and then it will start going back. Okay. So all you have to do is put different x value here, you get a different d value here, and then you just plot these equations. Next. For different x, you can just calculate different d's. Okay, so this is a calculate d's for different x. You put different x distance because you, for instance, if your town is, let's say, 10 kilometers from the mixing point, your x value is 10 kilometers. Okay, you put that value, then you get what's the deficit would be. So that in fact that's the many questions in the homework. Okay, and a lot of times you are asked to calculate what is the time or what is the distance where the concentration is the lowest. Okay, and the way to calculate is basically at that point is, if you see how the deficiency is changing, it's first decreasing, and then this is an inflation point. After that, the deficit is decreasing. Now deficit is increasing, and then it's going to start increase. So this point, if you take this curve derivative, that's the calculus where if you take the derivative of this curve, this is equal to 0. That means at that inflection point, critical point, dy dt or dd by dx equal to 0. At x equal to x c. If you take the derivative, which is basically slope, this slope is going to be 0 at that spot. So if you take the derivative of this one and put x equal to xc, you get these answers. Okay, you solve for xc. So if you take the derivative, I'm not going to do it, but I'm just going to write the equation directly. You know what is d? If you take derivative, that's going to get these answers. Okay, so this is how it is solved. So any times you are given a questions, everything's are given. All these numbers are given to you. The only thing that's not given is the concentration DO at this point. Then you can calculate all these value. If you calculate deficit, you know exactly what's the DO. because deficit is saturation minus the DO, and critical temperature is this. So you just plug in the value. Okay. So let's solve an example so that you know how to do it. Okay. All right. So that's all for the dissolved oxygen or BOD. So now that's end the surface water. Now there are a lot of questions that I put on the slides, which you will be solving. I'll help you solve some questions, but let's have some quiz question based on what we. So there will be a quiz on week 6, and there are some example quiz question like this. So read these questions. If Henry law constant or the Henry constant for oxygen is 769 liter atmosphere per mole, the expression for Henry constant is this. So I'm asking, is this Henry law constant is dissolved concentration of oxygen in water to air or air to water? So I say the statement is true or false. Based on unit, you can predict that, whether this is water to air or air to water. So if it is true, then (769 liter) by writing that, you can see whether that's correct or not. So what is the right answer, true or false? 50%. Okay, raise your hand if the answer is A. I'm not raising my hand, okay? I'm just asking you to raise your hand. Raise your hand. Obviously, nobody raise a hand. Raise your hand if it is answer is B. Okay, so well, many of you didn't raise your hand. You still receive 0 if you don't answer any questions, okay, in the quiz. But here the answer is false. Okay, so let's see why it is the case. If it is true, think of what's the unit of ATM. ATM is atmospheric pressure, is the unit of air. So if you write this one, you can write the same thing as ATM, mole per liter. Okay. ATM is a unit of concentration in air. So this is oxygen in air. Mole per liter is water, right? Okay, most. So oxygen in water. So that means this unit is given as air per water, but I say this is water to air. So that means it's false. All right, next quiz. Ultimate BOD is more than theoretical BOD. True or false? Raise your hand if it is A. Raise your hand if it is B. A lot of times I must say this one. When I don't know the answer, I look at other people and I see, okay, a lot more people, let me raise it. So I understand, but here it's very important for you to also share what the confusion is, because you will have the same confusion like many other students. So if you feel like the answer is opposite, feel free to share your thought process and we'll learn from it. And you also learn how to correct it. Okay, so it's very important to have this discussion. My goal here is not to have the right answer here. Also know why there could be a wrong answer. Okay. All right, so theoretical is basically saying that if you burn all the BOD, how much oxygen is going to go. But ultimate is how much of that BOD can be destroyed by microorganism. Okay. So theoretical is everything, but ultimate is what can be of that whole thing, what can be done by bacteria. For instance, if you put a plastic, theoretical oxygen demand is basically if you burn that, whatever the mass of the CO2 will release, that's the oxygen. But ultimate BOD is 0 because plastic cannot be eaten by bacteria. Okay. All right, next quiz. BOD degradation rate KD. Identify the terms that KD doesn't depend on. So the KD is the degradation rate. So that's basically LT. This is the KD that talking about here. I'm asking, that's the degradation rate of BOD or the chemicals. What are the factors that do not influence KD? Raise your hand if the answer is A. B, some and C, some, D, few. Okay, so there is a mix, but it's kind of, this is where it's a good thing because now we have a lot of confusion here. But most of you raise the hand for C, because if you don't trust me, we can do next time. I can show the picture here. Okay. And let's think of what is the right answers. Temperatures. All KD is degradations. Degradation of organic. So this C plus O2 go to CO2, right? So this C is degrading. The source of C. That's basically driving these reactions. So degradation rate of anything is done by bacteria, right? So that means bacteria control it. So microorganism cannot be the answer because they control the degradation. So this is not the right answer. They control it, right? And microorganism loves warmer temperatures. If it is too cold, decomposition does slow down. That's why you freeze stuff in the refrigerator. You don't keep it outside. So this cannot be right answer. I just told you that plastic cannot be degraded by bacteria. So that means what type of organic carbon does influence how quickly they can degrade it. So this cannot be right answer. The only thing remaining is water velocity. But I can tell you where some of you might have thought of how this is going to influence it. Well, if you think of water velocity, so bacteria need oxygen, right? They need oxygen to destroy stuff. So you might be thinking, okay, well, the velocity is more. We learn from the other process that reoxygenation rate would depends on velocity of water, right? So Kr is directly proportional to water velocity. But that's Kr, not Kd. Okay. Bacteria do not experience that velocity. They will just live in that one little bit. They're very tiny. So that's the reason why this is the right answers. Next question. Identify, oh, this is the same thing. I want to select this and do it. All right, another quiz questions. If BOD5 is same as BOD ultimate, what I'm saying here is that BOD5 you measure in 5 days is same thing as BOD ultimate. Which statement is true? Kind of a tricky questions, but that's why I wrote this equation here. Okay, so if this is BOD5, so all I'm saying is BOD5 is L0 this is the equations, and here I'm saying BOD5 is same as L0. This is the condition. I say that this is true in this particular problem. If that's true, what is actually happening here? If this equal to that, then what this term become? That's the answer. All right, so raise your hand if the answer is A. For B, you don't look back because you are the disadvantage most. You can look back, okay. All right, so this is a fun thing, okay. Whatever your answer, it's important that you engage, right? So nobody will answer this question the very first time. So it's important to know the thought process. So this is more like a mathematical question now. So if you put this value equal to that, if you plug this value here, Let me write it here. So that means this is going to be L0 is L0 1 equal to e minus KD 5. So that means this is equal to that. When exponential term become 1, when this is equal to 0, right? So that means the KD is 0. And when this can happen, that's the answer here, whatever the answer. When KD, when the degradation doesn't occur at all. Flow rate is low, BOD ultimate is very low to begin with. Microorganisms are hungry. Oh, now I'm confused. None of those actually explain KD equal to 0. Okay. So let's see what the real answer is. Now we have to think of different way. So what you're doing is you have started with a BOD. Whatever the initial BOD was, it's all consumed in 5 days. So that means in 5 days is sufficient to remove everything. Whatever. So what it means that you didn't have enough BOD to begin with to finally find something that's remaining. Because in BOD 5, this assumption is that L0 is so high that you'll always get something, right? If you don't get this one, then there is no value of this. Okay. So what it means that very hard to explain right now, but the answer is, another way to say is, if the BOD is not sufficient, you cannot measure BOD 5, because you have to get something at the end to be able to calculate BOD 5. It's always about what is initial minus final. It's very low, you can't detect it accurately. I'm glad this is an example quiz, because obviously if it is a real quiz, it will be a little more difficult to understand. Okay, so this is the last example. We are going to solve it. I'm not going to solve it, but I'm going to show it how you can use this equation that we just learned to solve this question, because that's the last questions you are going to solve in homework. Just below the point where the continuous discharge pollution mixed with a river, BOD is 10 milligram per liter. So basically you are saying there is a river, the waste is dumped here, and after mixing, the BOD is 10.9 milligram per liter, and DO at the mixing point is 7.6 milligram per liter. The temperature is 20 degrees Celsius. Deoxygenation rate KD is given. Average speed is given. U is 0.3 meter per second. Depth is given. All right, so it asks, find the time and distance downstream at which the oxygen deficit is at the maximum. Okay, so I ask in that equations, if you see that equation, this is the mixing point. The deficit or the DO is going to decrease with time. And at some point, this is TC or XC. I'm asking at what distance in the downstream the deficit is going to be the highest. Okay. So that means from here, I'm asking TC or XC. Okay. XC is basically velocity by TC. This velocity over time is, hold on, something wrong. Velocity times TC. So if you know one of them, you can solve the other one. And TC, if you see this equation over here, TC is this. KR, KD, everything. So everything is given. KR is given, KD is given, all of those are given to you. You calculate L0 in the previous questions. So you just plug those value and get the answers. Okay. So really there is nothing new to here. Everything is given, you just calculate value. So I'm just going to write for sake of it, so then we can leave. Is there any way to, any of you wrote these equations? KR by KD, it will take me a while. You know what, I don't have to write it again here. I'll write after, before I put it. But now you know how to solve all question on surface valve. Okay. And solve these example questions. These example questions will help you solve the midterm questions as well as homework. Okay.